I just want to mention that you can also do a two-factor ANOVA that is unreplicated. For example, Zach had a whole lot of germplasm that he tested over different localities, but they were unreplicated. So what we did is we did a two-factor analysis where we took the 5 seasons and we took the results of the cultivars. And you can do this on Excel even. And essentially what the analysis does is it uses the seasons as the reps for the cultivars, and it uses the cultivars as the reps for the seasons. It's basically, there is no interaction. It cannot work out the interaction, but it can still give you a reasonable idea of how the different cultivars are reacting. And again, here you can see a very low probability value, high F value. Seasons also had an effect, okay? But you can then do the LSDs and you can do the normal analysis, okay? The only thing is you don't have the season cultivar interaction. So somebody asked me, I said unreplicated trials and so forth. If you have enough localities or repeats, you can actually do an analysis of variance for unreplicated data. It's a factorial design, except that you're not getting the interaction value in your analysis of variance. So I just want to throw that one in there as well. So you can then put out a table like this. You've got your varieties, cultivar 1 and 7, and you can put your A, B's, and C's. So 1 and 7 didn't differ. 2 and 3 didn't differ, but they differed from those, and so you can then do your separations. And you can do the same thing for seasons and see that that season you had less disease, that you had more disease, and you can then start using that to do various other analyses as well. Okay, so you've got the unreplicated factorial, if I can put it that way. Now what happens though is when you start doing factorials, if you've got 10 varieties and you've got 4 fungicides and you've got 3 fertilizer regimes, you're starting with, what did I say, 10 varieties, 3 fungicides, that's 30 times 4 fertilizer regimes, your trial is going to get extremely large. And it's going to become unmanageable, and you're going to have the potential of sources of variation creeping in. One of the ways in which you can reduce that is by doing what we call the split plot design. Now, split plot design is exactly the same as a vectorial design, only different. Okay. And I'll show you what the difference is. Basically, what you're going to do in a split plot design is you're going to have a main plot. So the main plot would be fungicide 1, fungicide 2, and whatever, and the control. And within each of those plots, you split it, and you'd have your cultivars. And you're randomizing, of course, you have to randomize it, and you'd randomize over blocks. So what you're actually doing is you're getting, or you're setting up the trial so that you can measure the potential interaction between fungicide 1 and cultivar 2 and fungicide 2 and whatever cultivars. Okay. But what you are doing is you're actually saving space. Okay. So you're laying out your factors in a way which minimizes spatial variation and also makes it more manageable. So I'd have a main plot like in the middle here, and I'd spray my fungicide number 1, and then I'd plant my varieties. Okay. So the block is then essentially split, main effect and subplot effect. Okay. And those are the terms that we then use. I would then do my analysis using a program that takes into account split plot effects. And what the program essentially does, it throws out 2 analyses of variance in one, if I can put it that way. So what you have here, because the fungicide was the main effect, you've got the fungicide trial there. It has its own error or residual. And if you're doing fungicide comparisons, you do it relative to that residual. So your variance ratio and your F probability is actually worked out according to that. And then you have the fungicide cultivar interaction with its own residual, and you do your cultivar or your subplot comparisons and your interaction comparisons relative to that residual. So essentially a split plot is two analyses of variance in one, if I can put it that way. Okay. But the conclusions would be exactly the same as if it were a factorial design. Because what this is then telling you here, based on that F value and the probability, is that the fungicides differed significantly from one another in terms of whatever you were measuring, disease, or it would be disease if you were evaluating cultivars. Okay. It tells you here that the cultivars differed significantly from one another in terms of the disease that you were measuring. And what this tells you here is that there was a fungicide-cultivar interaction, which then is the same conclusion you would have reached had you done a factorial design, that the cultivars react differently to the different fungicides. Okay, so it's exactly the same principle, except that it becomes a trial design that is more manageable. If you've got small plots, and this now is cultivar 1 and fungicide 1, and I've got to spray this one, and then I've got to find the next randomization to spray cultivar 2, and you've got spray drift, and you've got all kinds of things. You have a chance of error creeping in, and you're creating more variation. Whereas with this, I can spray the one block, I have less chance of drift and everything else, and I'm minimizing variation and error. Okay, so the principle of analysis of variance is the same. The trial design is such that I can optimize my treatment effects and minimize my residual effects. Okay. So that's the whole point of these different trial designs, is to minimize error and maximize your treatment effect. And I can put the results in a matrix table like this. I've got my fungicide 1, 2, 3, 4. I've got my cultivars. I have my means, and I can then work out the LSDs. Now they can become a little bit complex. There's the LSD for, which one is that now? That's to compare two whole plots averaged over all the subplots. Then you've got compare two subplots averaged over all the whole plots. Compare two subplots for the same whole plot. So there are different combinations of LSDs depending on the comparisons you want to make within each of these tables. So each comparison you make has its own LSD. And that can become quite complex. And I'm getting a beady eye on the left-hand side here. My time is running out for today. But it's in the notes, and you can see that here, for example, you'd use the error A. There you use error B. So depending on what the comparison is and which component of the analysis output you're using, you'd use the appropriate error mean squares. Okay, and you'd work out your LSDs, and then you can do the various comparisons in that table. So essentially exactly the same as a factorial design, same principle. The design is then just to minimize error, minimize or reduce size, and to make the trial more manageable. Okay, hopefully that makes sense. And as I say, some of the LSD calculations can become very complex. You do have some programs that will work them out. If it's a sophisticated stats program, if it's a less sophisticated stats program, you actually have to go and do it manually. Okay. But all the formulas are there to make the different comparisons. Maybe on that point, and I'll pick up on this tomorrow. Okay, I think that's a reasonable point to stop. And okay, if there are any questions or comments or...
Let's thank Neil for his presentation here.